Swayam Prabha. Digital India. Educated India.
Hello again. Welcome to Basics of Noise and its Measurement. This is the first week and the second module of this course. And what we are going to cover today is this. What is sound? Before I discuss in detail as to what is sound, what is the meaning of sound, I would like you to look at this particular video. So this is about a minute and a half long video, and please look at it and think about it as you watch it as to what's happening and why is it happening. So what you see in this video is that you have a glass, a glass which can be used to drink some juice or wine or some drink, and the glass is empty as you see it, and all you are doing in front of that glass is playing a particular frequency, subjecting this glass to a particular sound of a particular frequency. So, and what you see is that at that particular frequency, if you increase the amplitude of the sound, the glass starts vibrating significantly. And because glass is very brittle, it cannot absorb a lot of vibrations. So even small amplitude of its vibrations causes after a certain amount of time for the glass to explode or crack. So just wanted to get you into this whole area of acoustics and think about it as to how if expose let's say a glass made of earth, a kullhad or something, pottery, and if you do the same experiment, will you be able to accomplish the same goal or not? Or if you use a glass of styrofoam or paper, will you be able to accomplish it or not? So think about it, and maybe later in the course I'll explain that what works for a glass made of glass may not work for a paper cup or paper glass or a styrofoam glass or a glass made for earth, and why. So that is all I wanted to show in context of this particular glass. And now what we are going to discuss are two important words. The first word is vibration and the second word is a wave. And what I would like you to understand is a very clear sense of what is the meaning of vibration and what is the meaning of this term called wave. Because in context of sound, both these terms are important. We say that sound is a particular type of a wave, but then these waves are generated when some particles are vibrating. So that is what I like to show you. So the first term is vibration. And what happens in vibration is that if you have a particle, whenever we are talking about vibrations, we start with this notion of a particle which is vibrating. So you have a particle, and this particle may vibrate around its mean position. So let's say this is the mean position. So it may vibrate up and down, or it may vibrate left and right, or it may vibrate at some angle. So vibration, when we talk about, it's about specific particles moving up and down, or back and forth, or sideways, or whatever, about a particular mean position. Now, if there was just one particle, then there would not be any wave. Wave is generated when we have more than one particles. If we have more than one particles, and if all these particles are somehow physically connected, then if one particle vibrates up and down, and because all the particles are physically connected, then the particle which is standing or sitting next to this particle, the original particle which was vibrating, that gets excited. So the energy gets transferred from particle A. So let's say these are different particles. So energy gets transferred from particle A to B. So this also starts vibrating, maybe a little later. Once particle A has started vibrating, it takes some amount of time for energy to travel from point A to point B. So you have transfer of energy in this direction. Then once particle B starts vibrating, then again this energy, because B and C are also physically connected, so you have excitation of particle C. Again, it happens a little later than the point of time at which B started vibrating, and so on and so forth. So you have transfer of energy in this direction. Okay? So this transfer of energy is associated with this thing called a wave. Now remember that particles are vibrating about their mean position. So it's not that particle A is moving to point B, to moving to point C, and moving to point D, and so on and so forth. The particle is more or less fixed at its mean position. It's not moving from one mean position to the other mean position. But what is happening is that energy is traveling, and it can travel very long distances, while particles can remain vibrating in about their mean positions and not shifting their mean positions. So I will show you an illustration of the same phenomena in this video. Now this is these are some animation pictures courtesy of Dr. Dan Russell, Kettering University, and these are very nice animations. So let's look at the animation which is on the top. So what you have is a number of persons, let's say, in a stadium, and what happens is that you have this person, he or she gets excited by the sight of let's say some game, and the person stands up and sits down and yells, and the excitement gets transferred from this person to the adjacent person a little later, and so then the second person gets excited, and then that excitement or excitation gets transferred to the third person, and so all these individuals, they are moving up and down in this case. So they are moving up and down vertically about their mean positions, but the energy is getting transferred in the horizontal direction, if we can call it the x direction. So what you are seeing here is that energy is getting transferred in the x direction or the horizontal direction, while the particles, or in this case the people, they are getting excited in the vertical direction or along the y axis. So you have vibration of individuals, while the wave is exciting the whole. The wave is exciting the whole. Fairly similar phenomena is happening to this long string. So let's say this string is free at this end, and I'm exciting this string at this origin. So what happens is, first this particular point get excited in the vertical direction, then a point little which is a little comes a little later, and so on and so forth. So the transfer of energy again happens along the horizontal direction, while the motion of the particle or particles which make up this whole rope or the string is in the vertical direction. Now, if again, as I mentioned earlier, if these particles were not mutually connected, then this transfer would not happen. So it's important that for a wave to propagate, the particles have to be physically connected to each other, otherwise the wave would not propagate. So that is what we see in this video, and you may have learnt it in your earlier classes or in colleges, that if the particle's motion is at 90-degree direction, in this case in the vertical direction, and the relative to the direction of the wave, then that type of vibration or that type of wave is known as the transverse wave. It's known as transverse wave because the direction of propagation of energy is in the transverse direction with respect to the motion of the particle. Now let's look at the third situation, the third picture. And what you see here is a red piston, and this piston is moving, it's getting disturbed slightly, and the whole tube is filled up with small particles of air or say dust or smoke or something. So what happens is that when this piston moves a little bit forward, it pushes the air particles which are just touching the piston, and these particles also move a little bit further. But once the piston moves back, then these particles come back to their original position. So the particles are moving a little bit further forward and then go back to their original position. But as they move forward and then go back to their original position, they also disturb particles adjacent to them, and the particles which are adjacent to these particles, they disturb particles further downstream, and consequently the disturbance or the motion energy or the kinetic energy of these particles, it travels in the horizontal direction or in the x direction. And it just happens that in this particular example, the direction of motion of particles and the direction of the wave or the disturbance of particles or the energy is getting transferred in the horizontal direction or in the x direction. So because here the motion of the particle and the transfer of energy direction, they are both aligned, this type of wave motion is known as a longitudinal wave. This is known as a longitudinal wave. Now, there is no reason to think that you can have only two types of waves, longitudinal waves or transverse waves. There could be all sorts of waves. So, but before we do that, let's look at some more animation, and this is important. So what we are seeing here is that you have in the top portion of this picture, let's say you have a rope which is initially static, and then this point gets disturbed, and then what we are doing is that we are looking at the motion of this red dot at this particular value of x. Let's say horizontal axis is x and the vertical axis is y. So initially the rope is fixed and it's not moving at all, and then there is some excitation at this end, and this excitation propagates, the particle gets excited, and it keeps on getting excited, and then the excitation of the rope stops. So after a while the motion of the particle also stops and everything becomes flat. So now what we are doing is we are plotting two graphs. The first graph we are going to plot is about the motion of this particular particle along the time axis. So in the x direction we are plotting time and in the y direction we are plotting the physical amplitude of the particle, the motion, how much the distance by which the particle moves up or down. So initially the particle is not moving, and then all of a sudden it starts getting excited and moves up and down. So it keeps on moving up and down, and then again it becomes static because it's not getting excited anymore. So this is the first plot which we are looking at, and that is the time behavior of the particle at a particular value of x, and in this case the value of x corresponds to the location of the point, and that is in this case a number 10.25 centimeters. Okay. The second thing what we are going to look at is, so initially we just looked at a particular point. Now what we are going to look is a picture of the whole wave at a particular time. So so on the x axis we are going to plot the position. Position means the value of coordinate, the x coordinate for the entire rope, and on the y axis we are going to plot the amplitude of each point on the rope, but at a given time. So initially everything is flat, and then we are taking a picture of the whole rope at time is equal to 27 seconds, and then what we see is that initially when t was 0 everything was flat, but at time t is equal to 27 seconds we take a picture, and the picture looks like, we'll see it here, it looks like this, so it's up and down. So this is frozen in time, and this particular picture is frozen in space. So what typically we express these two behaviors in time as well as in space in terms of a wave function, and that is explained here as sin omega t. I just want to make sure that I don't get different terminologies. So this is the wave function, okay, and this is what it looks like, at least in the context of the motion of the rope which we were looking at. This is the amplitude of this wave, this is the angular frequency of the wave. This can also be expressed as 2 pi times f, and this is the position of the wave, x is the position, and this is known as the wave number. Wave number. Okay. So when we are talking about waves, we are not talking about motion of a single point, but we are talking about motion in space as well as in time. So it has a time component to it and it has a space component to it. So now, as I mentioned earlier, there is no reason to presume that waves can only be of two types, longitudinal or transverse. I mean, those are the types which we have read about in our BTech or BE programs, but there are several types of waves, and what I will do is I'll show you a picture of another type of wave. But before that, there's this question: is particle velocity in a wave same as the velocity of wave? And the answer to that is no. The wave velocity is the velocity of the propagation of energy how fast energy is getting transferred from point A to B to C to D and to E. So that can be significantly different than the velocity of the particle. In a lot of cases, particle velocity is probably not as high as the velocity of the wave. So these are longitudinal waves, and here what you see is that particles and waves move in the same direction. Both of them are moving in the same direction. Both are aligned, so they are longitudinally aligned. And then you have transverse waves. So I can take a sheet of paper and I can vibrate it like this, one end, and as a consequence, the energy gets transferred in the transverse direction with respect to the direction of the motion of the particles. So that is why they are known as transverse directions. So we have these waves where particles and waves move in mutually perpendicular directions. And then you have a third type of wave. And what you see here is a bunch of dots, and you have focus on the motion of the blue dot, and what you see is that the blue dot is moving in a clockwise direction. So it's not moving in the longitudinal direction or the x direction. It's neither moving in the vertical direction only or the transverse direction, but it is having a motion which is circular in nature. And then there is another blue dot below the top dot, and that particular dot is also, or that particular particle is also moving in a circular way. It is also moving in a circular way. And what you see, if you observe carefully, as you keep on going down from top to bottom, all the particles are moving somewhat in a circular way, but as you keep on going down, further down towards the fixed end, the motion, the amplitude of the motion of the particles, or the radius of the circle which is covered by the particle, that particular radius, it keeps on shrinking. It keeps on shrinking. So the amplitude of the motion keeps on going down. Now, these types of waves, if you think about it, you would find in water. So suppose you take a bucket and fill it with water and make sure that water is stationary, and you drop a piece of chalk in it in the center. Then you will have these types of waves generated. So once again, you will see that in this case, the particles are moving about a particular mean position, but the energy gets transferred. In this case, it is getting transferred radially outwards, especially in water waves. It's a radial transfer of energy. So these are water waves. Then there's another wave, and this is somewhat similar but also different in a very specific way than the waves we just now saw. And these waves are known as Rayleigh waves. And look at the motion of these two particles which are colored in blue. So you have the top particle, and it's moving like this. That is in an anti-clockwise direction, and the amplitude is, let's say, something. And then you have this other particle which is further down into the material, and that is moving in the clockwise direction. So you have one particle moving in an anti-clockwise direction and another particle moving in the clockwise direction, and you see the same type of phenomena happening for across the whole band of this material for which we have plotted the particles. So these types of waves are known as Rayleigh waves. Once again, the energy transfer is happening from across the whole material, but the particles are moving either circular circularly either in a clockwise way or in an anti-clockwise way about their mean positions. So these types of waves are known as Rayleigh waves, and here you can interpret it as that they are moving in longitudinal as well as transverse directions simultaneously, but some particles are moving clockwise, others are moving anti-clockwise. The ones which are on the top or the free surface, they have larger amplitude of motion. The ones which are at the bottom, they have somewhat lesser amplitude of motion. So that is what these waves are about. So now that we have seen all sorts of different types of waves, not necessarily all sorts of waves, now let's think about sound waves. So what is sound? It is a small disturbance in a fluid medium. So if you have a fluid medium which is at rest, let's say I'm standing in this room and there's no sound in the room, and I'm standing still, air is not moving at all, then there will be some pressure of air in the room. And if there are standard conditions, then the pressure of the air will be 1 atmosphere, which will be approximately 101 kilopascals. And then I make a sound. So initially there is no sound, no disturbance in air is not moving, air is still, all particles of air are not moving. And then I talk, or I do tick. And then because of this sound, there is a pressure fluctuation in the pressure of the air. So that is what physically sound represents. It represents a small disturbance, and please be aware that we are talking about small disturbances, not large disturbances. Small disturbance in a fluid medium, and this small disturbance causes fluctuations, and again these fluctuations are small. It causes fluctuations in pressure, it causes fluctuations in density, displacement, velocity, and temperature. So this is what sound physically is. So that's what is shown in this picture down there. So you have a medium, and this particular medium is getting disturbed at the left end, and as this gets disturbed, the disturbance moves to the right side, and this type of transfer of energy in air due to longitudinal waves is referred as sound. And if we have to measure this sound, it essentially means that we have to measure these small pressure fluctuations. So we should have an instrument which is fairly sensitive to very small pressure fluctuations to measure sound, and typically that is measured by microphones. The velocity of sound, that is the speed at which the disturbance travels from point A to point B in air due to these sound waves, is known as the speed of sound. And at 20 degrees centigrade, its value is 343.2 meters per second. So that's the nature of sound. You have a total pressure, you have air, and in the air you have ambient pressure P naught, which is so many pascals, roughly 101 kilopascals. And if there is no disturbance in the sound, then that is the pressure of the air. And when you make a disturbance, when you talk in it, or you create some noise or create some sound, then there's an additional pressure. This pressure could be fluctuating. It could have a positive value or a negative value depending on the time. So you have a fluctuation in the pressure. So the total pressure is P naught plus P. And this P is the pressure exerted due to generation of the sound. So when we measure sound pressure, we are actually measuring this particular P. We are not measuring P total, we are not measuring P naught, we are just measuring this differential pressure with respect to the ambient conditions. So that is once again the nature of the sound. And these are different velocities. So sound is a pressure wave, we have discussed that. And then what we have listed in this table are speeds of sound in different media. For instance, if you have air at 21 degrees centigrade, the speed is 344. In water, it's 14 fresh water, it's 1480 meters per second. But if you go to ocean, and if it has, because it has some salt, let's say 3.5% salinity, then the speed of sound goes up a little bit. So it goes up to 1520. Sound in human body, since we are made up mostly of water, so sound propagation velocity in human body is fairly close to that in water, and it's about 1558 meters per second. And in wood and concrete and mild steel, sound travels much faster. So in wood it's 3350, in concrete it's 3400, and in mild steel it travels really fast, 5000 or close to 5 kilometers per second. And its velocity in glass also is somewhat very close to that in mild steel. So just wanted to give you a perspective of different sound propagation velocities in different media, and I think it's important to at least memorize or remember at least two different velocities. How fast sound travels in air at room temperature conditions, about 344 meters per second, and how fast sound travels in water. It's about 1500 meters per second. So it's important to internalize these two specific numbers, because in your daily life you may be using these numbers fairly regularly if you are actually involved with sound related measurements or noise related measurements. So think about these, and I think this brings us to the conclusion of this particular module, and look forward to having you in the next one. Thank you very much.